Okay, this is all that I wanted to say about the execution semantics of VHDL. Next, I'd like to move into the discussion of the value sets that we are using for the simulation of VHDL. Now, how many values do we consider when we do these simulations? Well, any digital computer could be described at the analog system level as well. We could use Kirchhoff equations to model these systems at the analog level. However, a complete analog simulation of a large computer would be infeasible in acceptable amounts of time, because this simulation would take much too long, and therefore we try to avoid this analog simulation. So therefore, we try to simulate digital computers at the digital level, just considering as possible logic values ones and zeros. However, we might still try to capture some of the effects of the underlying analog system, and we will have to see how we can capture some of the effects of the underlying analog system without actually using this very time-consuming analog simulation. So that's the overall idea. So how many logic values should we use for modeling, for really capturing the behavior of realistic systems? Well, we could think of using just ones and zeros. However, if we look at actual circuits, we have to realize that in general we have to distinguish between what we call the logic level, which is a kind of abstraction of the voltage, and the driving strength, which is a kind of abstraction of the current drive capability of a system. These two may be different, and we will be encoding these two in so-called logic values, and we will consider more than just two logic values. What I'm going to present you here is a very brief introduction into the so-called CSA theory that was published by John Hayes many years ago. And this CSA theory has its name because the basic components are so-called connectors, switches, and attenuators. And at the very end, we will see that the background with respect to this CSA theory will help us to understand current VHDL standards. So what are we looking at? First of all, let's consider the very simple case where we just have a single signal strength, and where as logic values we are just considering 1 and 0. Both are of the same strength, and from a logical point of view they are encoding false and true. So that's a very easy situation. However, there are good reasons for increasing the number of signal strengths. One of the reasons is that in a real hardware we have many situations where some output needs to disconnect itself from the rest of the circuit. So for example, if we have a standard PCI bus, we might have different cords that we plug into the PCI bus, and each of these cords could be trying to drive the backplane. And of course, it would lead to confusion if all of these cords would at the same time provide some active signal to the bus. So we have to provide a mechanism which would allow one of the cords to actually drive the bus, and the others should effectively disconnect themselves. So one of the basic techniques for disconnecting outputs is the so-called open collector output. And we will see a little later on that there are also so-called tri-state outputs. So with open collector outputs, we have one transistor which can provide a path to ground. In case that transistor is conducting, we will actually pull the output towards ground. But if that transistor is not conducting, then it will effectively disconnect itself from the output, which means that if the input is 0 for this type of transistor, then the output will be effectively disconnected, and we could use this, for example, for the output of some card put into a PCI cord slot. Now, in other cases, it may be necessary to also provide an active path to the supply voltage, but still to be able to disconnect the output. That's possible with tri-state circuits, and this is a very simple tri-state circuit. In this tri-state circuit, we have two transistors as outputs that can provide a path either to VDD, to the supply voltage, or to ground. And we have to provide these two transistors with signals of opposite logic value. Now, there is an additional control signal, an enable signal, and if this enable signal is 0, then both these transistors will provide a 0 at their output, and if these both transistors are controlled through a 0 at their gates, they will both be disconnected, and that means this output will be disconnected. Now, this is a so-called NMOS output. In practice, in many cases, we will be using complementary transistors there to connect the output to VDD. In this context, we might be using a slightly modified circuit. A slightly modified circuit is this one, where, again, we are controlling the gates of these two transistors. However, in this case, the enable signal in one case is inverted, and in the other case, it's not inverted. So the situation that we find down here with these two inversions corresponds to exactly the same one that we have on the left. But on the top, we have an inverted situation, which reflects the fact that this transistor is also conducting or non-conducting, depending on an inverted condition there at the gate input. So these are circuits that we can use in practice for disconnecting the output. Now we would like to model this at the logical level as well. And we would like to figure out at the logical level what happens if we are connecting two signals, if we have two wires that we are connecting together. What we are trying to model there, we are denoting by the so-called sharp operation, and the sharp operation tells us what is the resulting effective value if we have two signals that might have different values. So the sharp operation is providing that effective value, and in order to model this disconnected output, we are introducing a so-called high impedance value, which is called Z, and the sharp operation will return the strongest of its argument. That means 0 will always be stronger than the Z, and 1 will also be stronger than the Z. And obviously 0 and 1 are both stronger than the Z. Now what we are returning here can be analyzed by looking at such a diagram where we are depicting a partial order, and in this partial order the sharp operation will always provide the strongest of its arguments. So in this case, if we are using these two arguments over here, then we will always returning a 0, and if we use these two arguments, then we will be returning a 1. Now, we would like to define the sharp operation for all the possible values, and therefore we need to define the sharp operation also for the case where we have 1 and 0 as the two arguments. And we can ask ourselves, oh, what would be the result if we connect a 1 and a 0? Electrical engineers would call this a shortcut, yeah, or a short. So we have a short in our circuit. We don't really know what happens with our circuit in such a situation. The only thing that we know is the resulting value will be a rather strong value, but we don't know really the logic value that can be associated with that. We are introducing a value called X, where the X means it's a strong signal, but we don't know which logic value should be associated with X. And we will include this X in our diagram depicting this partial order. And in case we have a combination of, say, X and 1, if we have these two as the arguments, then we will return an X, of course. If we have a shortcut somewhere, even if we link that shortcut to another VDD signal, we don't really know what will be the result. We can use this Z and the two signal strength values in practice. For example, there might be some bus to which we are connecting two outputs. So we have one output on the left and one output on the right. And we assume that for this output on the left, we are setting this enable signal to 0, which means that we are generating the Z here at this output of the left subcircuit, whereas the other output will generate some value depending on the function that's provided here at the input. So that means that the signal value on the bus will correspond to the sharp operation of these two arguments. And the one argument is C, so therefore we will be returning the other argument as the value, and the whole circuit would behave as if the left output would not be there. Okay, there might be the question, are two signal strengths enough? And if I'm raising this question, this might already lead to the assumption that, well, there may be a reason for having more than two signal strengths. What could be a reason for having more than two signal strengths? Well, if you know a little bit about implementing such digital circuits, you might already have heard about so-called depletion transistors. Depletion transistors are used in some circuit technologies to provide a rather weak path to the supply voltage, so that whenever this transistor is not conducting, we will be pulling that output to the supply voltage, but in a rather weak manner. So that means this so-called depletion transistor will contribute a weak value that would need to be considered in this sharp operation when we compute the effective value for signal A. And we will therefore introduce a weak 1. And we will call this weak 1 capital H. And the overall result from this sharp operation will be as follows. If we have as arguments a weak 1 and a strong 0, then the result would be a strong 0. And if we have a weak 1 and a Z, which is actually the weakest signal of all the signal values, then the result would still be an H. This would be exactly the situation that we would find if this transistor over here is not conducting. If F is equal to 0, then that transistor will not be conducting. And then from below, from this lower end of the circuit, we will be providing a value of Z, and the depletion transistor will be providing this value of H. And as a result, we would have this H as a value at the output. Okay. Now we can include this weak 1 in this diagram showing the relative strengths of the different signal values. And in order to be symmetric, we are not just introducing a weak 1, but we are also introducing a weak 0. Now the sharp operation also needs to be defined for the case where we have a weak 1 and a weak 0 as the arguments. That means we have a short between weak signals. Again, we don't really know what would be the resulting logic value. We only know that we would not be really sure about the resulting value. And this we denote by the introduction of a logic value called W, capital W, which is the resulting value in case we have a short between a weak 1 and a weak 0. And the sharp operation, again, will always return the strongest of the arguments used for that sharp operation. So if we have, for example, these two as the arguments, then the result would, of course, be a W. And if we had, let's say, these two as the arguments, then, of course, the result would be a strong 0. So in this way, we have now introduced three different signal strengths. We have the strongest strength, we have a medium strength, and we have the weakest strength. Now, the next question is this enough? And, you know, from the way that I'm asking this question, you might already get the impression, well, possibly not really. What could be a reason for introducing another signal value there? There is one good reason why we should consider another signal value, and that is the need to use so-called pre-charging. In many of the circuit technologies that are used for implementing digital computers, we have the situation that we can provide a zero on a bus in a rather short amount of time. We can discharge any charge that's there on some capacitance in a rather short amount of time, because typically these transistors that we are using for connecting something to the ground are pretty strong. But transistors that are at our disposal for connecting something to the supply voltage are typically weaker. So it takes a little longer. And that means that pulling this bus towards a logical 1 would normally take a little longer than pulling this bus towards a 0. Now we would like to avoid that additional delay in a rather smart way. And avoiding that additional delay in a smart way is possible with pre-charging. With pre-charging, we are adding a special circuitry to those wires where we see a very large capacitance. And in this case, we are pre-charging this bus during the times where we don't know the function to be computed anyway. So we assume that it will usually take some time to compute this function f, and during the time where we are still computing that function f, we are using that special transistors to pre-charge the bus to a logical 1. Now if it later turns out that this bus should actually be discharged, we can discharge that bus rather quickly. But we have to make sure that this signal actually is only providing stable values, because we cannot, by incident, discharge the bus, because if then later we have to recharge it again, it will take some time. So we need to be sure that this value f is only providing us with stable values, so that this transistor will discharge only if we are really sure that the bus needs to be discharged. So the signal values which are provided by this pre-charging logic are weaker even than the weakest logical signals that we have considered so far, except the value z, because z is still the weakest signal of all the signals. So in order to introduce and in order to consider these extremely weak logical signals, we are introducing a lowercase h, which is a very weak signal of the same logic level as a 1, but the driving capability is extremely small. So again, we are defining this sharp operation to correspond to the operation that I already showed for this diagram, showing the relative strengths of the different signals. We see that in this diagram, we have included these very weak signals down here. We have a very weak unknown, which is the result of connecting a very weak 1 and a very weak 0. And the resulting operation, the resulting value from a sharp operation would again correspond to the strongest value that we have among these signals. And it is the strongest, it is the weakest signal which is stronger than both the arguments. That's exactly what we do over here in this partial order, and actually we call this the supremum operation. So there could, of course, be the situation where as arguments we would be using, let's say, these two values, and then the largest, then there is the question, which is the resulting value there. Okay. I'm again raising the question, are 4 different strengths enough? Are there possibly reasons for using 5 different strengths? Well, and if I'm raising that question, then you might already get the impression that, well, there are arguments for using a fifth signal strength. And there is a very obvious argument for using a fifth signal strength here. It's the argument that so far we didn't talk about the power supply yet and the VDD voltages and the ground. Because these signals, these wires that we're using there, they provide signals that are even stronger than the strongest signals we have considered so far. So therefore, we might be tempted to introduce even more values. We might be tempted to introduce a very strong 0 and a very strong 1. They are of the same logic value as 0 and 1, but they are stronger than 0 and 1. This was actually done for a so-called 46-valued logic that was proposed in a very famous book on modeling digital logic based on VHDL. And for some time that book was very popular, but these days it's less frequently used. We could even go towards more strengths in this somewhat shortened course. I will not talk about Verilog, but in Verilog we can be using 8 different strength values. So this could even be extended beyond the 5 different strengths that I'm considering here. Now, what is actually used in practice? In VHDL, there is no built-in set of values, apart from the trivial values 1 and 0. There is no built-in set of values, and therefore each user of VHDL could use his or her own value set, which would be very inconvenient, because that would mean that one user could be using one set of values, another user could be using a different set of values, and then all this would become incompatible, and that would really be boring. So therefore, the designers of VHDL tried to find a way out of it. And therefore, they have defined a standard value set that can be shared between the different users. In the standard value set, we have the following values. We have 0, 1, Z, X, capital H, capital L, capital W, and additional 2 values U and a minus sign. These values are standardized in a standard called IEEE 1164. And in the standard IEEE 1164, the first 7 values are exactly the same values that have been described previously. So everything that I said about these 3 logic values applies, which means that we cannot really describe a combination of pre-charging and depletion transistors in IEEE 1164. We could possibly abuse these values to describe pre-charging, but then we can't really use these values for describing depletion transistors. There is only one set of weak values. So in addition to these 7 values that I introduced earlier, we have 2 additional values, and one of them is a value called U, where U corresponds to a completely uninitialized value, and the simulator by default will initialize all signals to that particular value, so that when you work with such VHDL models, you will then have a way of identifying that you didn't initialize a certain signal. So the U is easy to explain. It's a little more difficult with the minus sign, because the minus sign denotes the so-called input don't care. And first of all, I'm trying to explain what the input don't care is intended for, and then I will show you that unless we are using the most recent extension of VHDL, it cannot be really used in the way that we would like it to be used. So what is the intended purpose of the input don't care? Let's suppose that we would like to describe a Boolean function in VHDL. Let's suppose that we have a Boolean function where we have 2 terms, that describe how to compute that function. And we furthermore assume that this function should be undefined in case all these three signals have a value of 0. Then a very convenient way of describing this function in VHDL is to use a so-called selected signal assignment, where we have a signal assignment like before, and then we have a kind of select or a case statement. In this case statement, we are using the concatenation of these three input signals. And then, in order to describe this function rather conveniently, the idea is that we do the following. We assume that we would like to generate a1 whenever this first term is providing a 1, which means that we are providing a 1 if a is equal to 1 and b is equal to 0. And the idea is that we don't care about the third variable there. Yeah, therefore, we put this input don't care there. We do the same for the second term, where we specify, well, we don't care about the first variable, but we assume that but in case the second and third variables are 1, we would like to generate a1. If all the three variables are equal to 0, then we would like to generate an undefined value where actually this x is used in a different way than what we did before. So we are not really using the same semantics there for the x that we used before, because in this case the x corresponds to either 1 or 0. But it's not the electrically undefined signal. It should be either logical 1 or a 0. And otherwise, the output should be a 0. So the question is, will this work as intended? Well, it will not work as intended, because what the simulator will be doing is the simulator will check, for example, for the very first row over here, if a has a value of 1, if b has a value of 0, and it will check if c has a value of minus, which is just one of the possible values in a VHDL system. Now, we will never assign to C a value of minus. So therefore, this last test will always be false. And that means we will never meet this condition over here. We will never meet that condition over there. We will only occasionally meet that condition there. And that means we will usually only have a return 0. And the circuit would be minimized if we always return 0. It's a very easily implemented circuit. It's just a fixed wire connected to ground. Yeah? So that means this doesn't work. Since the simulator does not include any special handling for the minus sign, at least not for pre-VHDL 2006. So we see that the selected signal assignment is not really providing the function that we are interested in. And therefore, the standard is providing a special function called standard match, which has a special meaning. If we are providing this function standard match with a concatenated set of signals and a special value, then this input don't care is handled in the intended way. And in this way, we can implement something similar to the selected signal assignment statement, but we don't really have the flexibility that we have with the selected signal assignment statement. VHDL 2006 has changed it. There, the minus sign can be used in the intended way in these case selectors. So we see that the most recent version of VHDL is different there. Now, in the context of hardware modeling, we have this situation where we do have to model the case where hardware outputs are tied together. So just like in the case where we have this PCI bus where we can plug in certain cards, there we might have different outputs, different cards might provide different values there. And if we do a simulation of such a system, then we have to figure out what is the resulting value there if the different cards are providing different values. We could have two cards providing, for example, Z, one providing a strong 0 and the other providing a weak 1. Now, computing the effective value in VHDL is done with the help of so-called resolution functions. And resolution functions are designed so that they compute the effective values. Syntactically, they are included in descriptions of VHDL. Like, for example, in the standard, we are typically assuming that a standard called standard unresolved logic is defined, where we have these values that I just mentioned. And then we can define a subtype, standard logic, and there we introduce a name of this resolution function. And this resolution function is then a function which is computing this effective value. And in order to compute this effective value, it is provided with an array of arguments. And each element in that array corresponds to one of the outputs. And then in the resolution function, we would be returning a Z if nothing else is provided by any of the outputs. We would be returning the value provided by one of the cards if there is only one output. But if there is more than one output, then we will iteratively loop through all the outputs and always compute the strongest of the values. And we do this by referring to a table called resolution table. And this is the so-called resolution table, which provides us with results. And now, if you look at the VHDL standard, at standard 1164, you're just given this set of values. And this looks very confusing, and it's very difficult to understand what's actually the meaning of this, why certain values have been selected. However, if you analyze this more carefully, you will find that, for example, for connecting something to a 1, you will be generating a 1 in case that you are combining the 1 with 1, Z, W, L, or H. That means in all these cases, the 1 is the strongest signal. Now, however, if you combine this with a 0, then obviously the supranom computation generates this X there. If you combine this with X, then obviously that's the strongest value anyway. And that means if you're not considering for the time being these two special values U and minus, what this table is doing is it's just returning the supranom according to the partial order that's indicated there. So that means this table in the standard can be understood only, from my point of view, if you know the background, if you have the background of the CSA theory, because then you know what you're doing there is you compute the supranom in this partial order. That's easily understandable. And without that background, it's very difficult to understand why there are certain entries there in the table. And then you might wonder, well, where did we actually place this U? And if you look at this carefully, the U is actually there. It's actually more at the top of this X. So it's somehow even stronger than the X, because if something is undefined, then the result will always be undefined. Okay, so in this case, we see that the background provided by the CSA theory actually helps us to understand the standard which is used in practice. So this leads me to the summary for this set of slides. Today, I introduced the discrete event model as a paradigm that we can use for modeling systems. We have seen that this discrete event model, the semantics, can be implemented with a queue of future events, where we always fetch the next event there from the list of events. We execute the entry that we fetch there, And we also saw that this discrete event model is very frequently used for the digital simulation of digital computers. We saw that processes are used to model hardware concurrency. We also saw that signals model the communication that is implemented in wires in the real circuits. We saw in certain cases the use of the weight statement and of the sensitivity list. They indicated at which time we need to evaluate the body of these processes. And we saw this VHDL simulation cycle, and in particular we saw the importance of these delta cycles, and I explained why in VHDL we do have determinate simulation semantics. So that means these simulations should always generate the same result, provided that the input is the same. And then during the last minutes, I introduced you to a special case of multiple valued logic. I introduced you to a way of creating value sets for multiple valued logic. We saw the general CSA approach, and then we saw that this can be applied to IEEE 1164, and we saw that without the background it's very difficult to understand IEEE 1164. So this concludes today's lecture. Are there any questions? Thank you very much.